Okay, folks, so I did get somewhere in grading. But I still got the other one to do today. All right. Oh, it was right next to it.
Yeah, and
This is I like the blue.
Oh, no. But I kind of give you my work. I kind of like.
Yeah, I kind of separated them out. Hopefully got everybody in the right place. Cool, all right. I'm halfway caught up, and then unfortunately you're gonna give me some more to do. So, by Friday, I hope to get them all in the blackboard. No one's dying right now, so that's a good news. I don't expect anybody to. And if I look at grades, midterm should turn out to be fairly okay. Yeah, A's and B's, homework wise. Exams are, looks like A's and B's together, so. And I don't think I'm giving things away to you, so that's kind of a good thing there. All right, stuff we did, actually, the homework is due today. Any questions on that? And then we'll go back to bending stuff. You're looking for the centroids of the moment of the nurses, right? Anybody have a going party to these?
I have a problem with
That's when we go to that. That's the plan.
yeah.
As long as you remember where your baseline or center is, you're going to be dead center, or it's just going that way, or the bottom, which is where it is. All right. Anybody else with any other questions? Not, just slide them over to the center here and get them out of your hands and go from there. No, it's not. That's a good reason for it. Oh, give it up first.
Forgot to write all my answers on this side. Never had any class besides for this one asking for that.
It's a, old trick, but a good trick. And someday you may hate me, but it'll also be something that you'll look back at going, well, that made that problem easy when you got stacks of papers and you're trying to find things. All right, so, all right, we're not going to do one where we get to make it up this time. I decided that was just too much fun. But we are going to do something very similar to last class. So, anybody have any questions about what we did on Monday? Today's Wednesday, right? Okay. All right. So let's try this one. We got a beam. No, I don't actually want to do that one. I like it for the curves, but I don't like it for the way the solution goes. Hold on. Yeah, let's do this one. All right, so we got a beam. It's going to be attached to the wall. And we have a force here, 2 kilonewtons. We have one here that's upward, 5 kilonewtons. We have one that is not quite dead center, but three, 2, 5, 2. Okay. And we have 0.3 meters. Zero 0.3 0.3 meters there, 0.3 meters there, and out at the end, just because someone didn't like us, gave us 0.4 meters. Okay, we got A, C, D, E, and B. All right, and it's kind of a strange labeling system, but it's the way this particular problem laid out. When you do these in the real world, okay, you can choose your lettering system, and I would always go left to right and don't worry about it. Just A, B, C, D, E, and get to the end of it out there. Make sense? But we'll go with that. But it is a good idea to put labels on this thing, because as we start doing these things, we come up with a shear and bending moment diagrams. It's going to be interesting to keep track of all this stuff. Okay. All right, so that's the diagram for this. And what we want to do is draw Okay. And just to make sure I actually did hit record. We did, okay. All right, so far so good. Step number 1. What is it? Okay. So this is relatively simple from the standpoint of draw a line, put the forces in, okay? And what's next to this thing? We need a reaction here at A though, don't we? Okay. Okay. So FBD. Next thing is let's figure out what the reaction is, right? And if I assume up is positive, that leaves me an RA minus 3 kilonewtons minus 2 kilonewtons plus 5 kilonewtons minus 2 kilonewtons. Yes? I still got safety glasses on all morning. Okay. So solve for all this. RA is going to be equal to, so that was a negative over here, so that becomes a positive 3 here, plus 2 minus 5 plus 2. Everybody see what I did and why I did it and how I got away with it mathematically? All right, so what do we got?
RA equals 2 kilonewtons.
I do hope so. Okay. And it should be going up if we did all things right, so which means positive. All right. Now, there's one more piece to this that we need to figure out, and it's going to be how do we keep this thing from causing any other problems. We're going to need it for down the road, and you can introduce it now or I can introduce it later, but I think I'm going to introduce it no, I think I'll introduce it later. We'll do it when we get down to the moment stuff. Okay. All right, so the next piece of this puzzle is oh, how big does this diagram turn out to be? We can live with it right about there. Okay. All right, so our shear and its units are kilonewtons. Okay. And that's 0, by the way. All right. over to you for a minute. All right, so the shear section. We're looking for the forces that are going to cut things off, okay? So really, what's the first thing for the shear here is V at A is equal to RA, right? Which is equal to 2 kilonewtons, okay? All right, and you know, if I was smart, I would have drawn, let's do that again. Let's do the line at one of the regular lines here, and then we can actually have some fun with this. All right, so we'll make that 1 kilonewton. We'll make that 2 kilonewtons, okay? So the first thing I got to do is go up 2, right? All right. So if I plotting the shear, that's the only force until I hit the one at, oh, it'd be nice to put the letters in there, wouldn't it? Just to make sure I used them right. A, C, D, E, and B, okay? So the 2,000 newtons upward is steady all the way until what point? C, who said it? Don't be bashful. C. Is it just at C, just before C, or just after C? It's steady at 2,000 kilonewtons all the way until
B. C.
C. But I'm asking you to think about this. As it approaches C, okay, what's it going to be just before C? Remember? Okay. So it's actually going to shear at C, but up to C, just before it approaches there, it's still 2 kilonewtons, correct? Are you seeing that? If you don't understand that, what I'm going to draw in about 30 seconds is not going to help you. Okay? It's still 2,000 newtons all the way across this first 3 millimeters, or 0.3 meters, okay? So it goes right there, all right? So the next point I'm going to look at is VC, and that is VA minus the 3 kilonewton reaction at C, or the force at C, okay? See where I got that from? All right. So if I plug in the numbers in there, 2,000 kilonewtons minus 3 kilonewtons, and then I get a negative 1 kilonewton. So good so far? Okay. So literally I'm going down to here, negative 1. You following along there? Okay. Now, my next one is VD. Okay. And what's it going to be all the way until it approaches D? Negative 1. There's no other forces acting on or causing anything to happen, right? Make sense? Cool. All right, so I'm going to run that straight over to there. Okay. But the equation is going to say VC, and we're going to knock out another 2K negative at D. So that'll be negative 1 kilonewtons minus negative 2 kilonewtons. And that's going to be a negative 3 So far, so good. So we went down -2, -3. We're there. All right. Now this gets really fun on comp paper, by the way. I tend to draw, I should do one of these on comp paper so you can actually see it. I draw my free body diagram and my shear diagram, my moment diagram over in the left-hand column all the way down. And put all the numbers over to the right. Okay? People tend to do it a lot of different ways. As long as you keep the math straight in your head and you've got a diagram, I don't care if you take the whole front page and make a diagram. Okay? You need to keep the math running while you're doing the diagram. Okay? Just the way I was shown years ago, and someday I could actually probably ask Bob Merrill, why did he show it to me that way? But he did, and that's what we did. All right, so V at E now is VD plus the force at E, which is 5 kilonewtons, correct? So a -3 kilonewtons plus 5 kilonewtons, and we're going to get a +2 kilonewton we got to deal with. All right, so, and I missed my little conversation here. Everything over until E stays constant because there's no other forces acting and to cut it off. Okay? And then I'm going to go vertical up to +2. All right? And V of B will be equal to VE minus the 2 kilonewtons. Okay, so that's the force at B. So +2 -2, and we wind up with 0 kilonewtons. And we're going to wind up right back at 0. Okay? The coolest thing about this is if you don't end at 0, you did something wrong mathematically. Okay? With simple vertical forces, it's easy. When you start mixing in other things in there, it gets a little bit more complicated. Okay? But so far, everybody's kind of following along? Deloge? Yes?
So what does this chart help us find if we know it's always gonna end at 0?
We're looking for the maximum shear force in this case.
So that's not, so each one of those like plateaus is the maximum shear
At some point along the line. But the V max is -3. Okay? And we know it'll act over that section at 0.3 meters there between V and E. Okay? The other cool thing is, when we go to do the maximum moment pretty soon, we'll find out where they kind of occur. Keep that in mind, okay? I'll let that one linger for a bit. All right, so we're good, right? Everybody sees this? Now, you can do this any way you want, but I want you to remember these areas underneath this thing are what we're actually going to use to help us figure out what's going on with the moments. Okay, so you don't have to draw those in on your homework. Okay, that's just extra stuff just so I can do the visuals. Okay, unless you're really bored and you want to doodle lines. I had a student that would repeat it and erase it and repeat it and erase it because it wasn't perfect. I don't care. Actually, I was probably that student too once upon a time. All right, so we need to extend our shear or moment diagrams down, way down here so I can keep it someplace in perspective. Whoops, let's not do red. Okay. How high we gonna go here? 0.4, -2, 0.8. All right, so this is the moment, and this is kilonewton meters. Okay. All right, we're going to call that 0, and I'm going to do this in terms of, what am I going to do this in terms of? 0.2, 0.4, 0.6, 0.8. Negative 0.2, negative 0.4, negative 0.6, negative 0.8. All right, and you can choose whatever units you really want to play with there. All right, so now for the moment diagram. Okay. And to do this, we kind of need the stuff from up here. And this is why the calculations tend to start going this way. The only other way I could do it on here was if I started running the moment equations over to the right here. But literally, you're going to have to keep it somewhat on a page account paper. Okay. So put the diagram all on the first page, put all the equations on page 2, however you can make this sort out, okay? All right, so the area for the first one, all right, is really going to be 2 kilonewtons times 0.3, all right? Now, I got to go back here. This is what I was going to introduce earlier. All right, let me slide all the way up to here. So that was my vertical sum of the forces reactions, okay? But in order to keep this thing in space properly, we need a reaction on this. That's this. Okay, so we need a moment at A that actually keeps this thing attached to the wall. Okay? Now, strange concept to you, maybe? I'm hoping. What's that? Oh, you're using it so that we can actually figure out all the pieces and parts. So the three-body diagram up there is going to give us all the reactions that happen. Okay. Now, that beam in itself, if it was in outer space, okay, will it stay level? I was shaking his head no, but I think he thinks I think we're heading in the same place. But right now, just the beam itself, where'd my ruler go? Just hit Montana. If that thing is sitting there, okay, and it wasn't attached to the wall, would it just stay level with those forces?
No.
Okay, why not? Correct. It's going to want to move anywhere up and down this way, right? Do I see that? So in order, because it's attached to the wall, I have to have a reaction at the wall. But it's not an axial reaction on it, it's the moment, okay? I have to put a coupling on this to actually hold this thing in place at this point. And then it won't bend up and down, okay? It won't do this or it won't do that, okay? But without that out there, this is allowed to go up and down like this. And if it was outer space, the astronauts would just give it a little touch and go that way forever across the universe. Okay? with the moment on the end holding it, then it can. Okay, the only thing it can do is if the forces become unbalanced, it will start rotating. Okay, and then it'll just keep rotating about that point forever because there's no friction. Okay, so that's one of the greatest things about space and what the astronauts have to put up with when they're trying to build things. Okay? We got to come up with this moment out here first. Okay, and unlike a typical beam that we're using for like a bridge, there isn't one of those on a bridge because it's not doing anything to stay in that position. It can go this way or this way, and it all just sits there by weight. Okay? But we're going to hang this off the wall. I need something here. Okay? So I do have to figure out what MA is. Okay? So when I did the sum of the moments, or some of the forces here, I really need to come over here and do sum of the moments. In order to do that, do you remember that from statics? Yeah, okay. So we take our first one, our MA, and just to make life, oh, I don't know, which way do I want to go? We'll make that positive, okay? So it's counterclockwise. All right. So MA is, I drew it in that direction, so that's positive. But R3, the force at C is 3 kilonewtons, and it's at 0.3 meters, okay? And I chose negative, why? Because of what? The force is going downward, but which way is it going to try and rotate? Counter or clockwise. It'll rotate clockwise. Okay, so that's a negative. Okay, 2 becomes a negative also because it's going to kind of rotate there, but now we're at 0.6 meters. All right. All right. And now we're at 5 at point E, and that's clockwise with the direction of moment. So that'll be 5 kilonewtons times 0.3, 0.3, meters. And the last one is a negative 2, and that is at 9 and 4 is 13, correct? So 1.3 meters. Everybody okay there? I'm going to zoom in on just this section here so everybody can see it better. All right, so we just algebraically solved for MA. Move MA to the left. Change all the signs, which is, if I chose the other way, I could have eliminated all that. But we are plus 3 kilonewtons times 0.3 plus 2 kilonewtons, 0.6 meters, minus 5 kilonewtons times 0.9 meters, plus 2, I forgot the kilonewtons up there, 1.3 millimeters. Okay, and we get all done. We got an MA that should come out to be 0.2 kilonewton meters. Okay, and it is going in that direction, so counterclockwise. Everybody with me so far? Okay. The reason I needed to do this is when you're looking for the reactions, you really got to find all the reactions. Otherwise, you're going to assume we get the shear and bending moment diagram, it all started at 0. For a regular beam supported by supports on both ends, that will be the case. But for a cantilever, this won't. Good question. Just ask myself this question. You guys know the difference between a cantilever and a simply supported beam? Anybody ever talk to you about that any place in life? No. Okay. So, you know right now, I'm hoping that if I held this, if I hold it like this, I have simply supported beam. Okay? I can, here I can have Montana put a finger at 19. Right around this like a okay? So we are literally now supported in 3 places. Okay? Now if you think about this from a bridge design, this is a bridge that actually supports it to both banks, and then out in the middle of the river is, how big is that? Whoa.
Just pretend.
Pretend you're holding it there, okay. We have a, what's the term I'm looking for? An abutment out in the middle of the river to set the spans up, okay? And that would be that, okay? Now, if I slide my finger into, like, say, 7 meters, I'm still simply supported where I am at both ends, and we got another support out there. But everything to my right, past my finger at 7 inches, is a cantilever. A cantilever is something that hangs off something, okay? And literally, a cantilever is this. Actually, put your hand right down there. Cantilever does this. Get my finger out of the way faster. Okay? It can go down. Hold it down really tight now. It can go up. Okay? And that's all a cantilever is. Something that's not supported on both ends. Okay? They wind up all over the place. Okay? And you don't even know it. But literally, anybody want to join the bridge team, there's always a dumb cantilever design in there. Okay? Because what happens with the cantilever is we get to cause a lot of bending. Okay? In fact, do this. Hold it there. Put one hand right there. Hold it up. So if I bend this down, if you can see past his arm, everything from here to there is trying to bend upward. Okay? So I actually bend this way, and we cause an upward deflection in the beam. Wow, that's a whole new concept for structural analysis, okay? Thank you. You look pretty good at the model. Everybody kind of getting the hang of this? Okay. Now, that's a bridge, but that's the biggest one you probably can see and actually experience. But in the mechanical world, your car crankshaft is simply supported, bearings on both ends, okay? And then we put forces, 6 cylinders, so let's say 6 forces on this thing, okay? And it's not only not straight, it steps down, steps up, steps down, steps over, steps, it's moving on in different places all the time. Okay? Crankshafts are the greatest things to design. Trust me, stay away from them. Somebody else worry about it. But it's simply supported, bearing at both ends, okay? But, let me give you a but to this problem, okay? So the crankshaft has to operate in the same timing that the camshaft has to operate in, okay? So guess what sticks out of the front of your crankshaft? Yeah, we got about 3 inches out there. That's out there trying to stay where it's supposed to be. So all this back here in the engine, and we're bending the hell out of this with the gear on the end, okay? And then we're tying it up to the other one, and that's got a little support on it, and we got to worry about it, okay? So you're going to see them all over the place, okay? Porch decks, okay, can be built with a cantilever on it, okay? You can actually attach everything back in the house back here, and then you have that much of the supports sticking out in the middle of the space. They don't need columns out here if they're designed right, okay? 90% of the time, everybody doesn't design them right, they put columns out there, okay? Or they put columns because they think they actually need them, okay? So carpenters are just taught, oh, nothing hangs out in space. Yeah, it can. Waterfall for Frank Lloyd Wright, his wonderful little, you know, I never wanted to be the concrete engineer on that project because the entire house is one big massive counterweight just to support the room that hangs over the waterfall. It's like, really? Okay, give the architect what they asked for because you don't want to piss them off. And they pay you a lot of money. But there's an awful lot of concrete beam design in that went a long ways to make that happen. Okay. All right, cool. Should have thought about that earlier. Thank God, where does day go?
But like, if you have a porch that's just off in the space, and then you start putting weight on it, wouldn't the whole porch start to bend then?
Oh, yeah.
Oh.
Yeah.
So it doesn't sound very practical to do it that way then.
Well, but you have to counterbalance it and make it strong enough to withstand that. Same with your car crankshaft. You put the gear on the front of it to drive the camshaft above. That's no two ways about it. Okay. So that's where you guys are heading. So a little bit of machine design, a little bit of bridge design, and we're not going to get through that after this problem. So it's all there. I'm going to look some stuff up and see some problems to give you for over the weekend. I'll try to get them posted out so you can take a look at them ahead of time. And then ask some questions on Friday, but we'll try to work some more problems out. Okay? All right.